Alright, so today we're talking about section 2.5, which has to do with autonomous differential equations. We'll remember that those are differential equations of the form y prime equals f of y. Those are autonomous. And so autonomous means that the equation does not explicitly depend on t. All you see there is a y, right? And we saw that the what happened in the ty plane then, in the direction field, was that along any horizontal line, all the slopes were the same. Okay? Now, we should say that there's some special solutions. I think we've talked about these before as well. Special solutions to the autonomous differential equation are solutions that are at equilibrium. So equilibrium solutions are solutions for which y prime is equal to 0, or equivalently constant solutions to f of y equals 0, right? And so you can see, right, that if you have y as a constant, then y prime would be 0, and then if f of y is equal to 0, the differential equation is satisfied. And so those equations are called, or those solutions are called equilibrium solutions. You can find the equilibrium solutions in the direction field because they'll just be solutions that are horizontal lines. Good. All right. Now, just as a side note, we already know how to solve these kinds of autonomous differential equations analytically. And that's because they're separable. The function of t, or the function of x, is just equal to 1. And so to solve, you would just take 1 over f of y dy equals dt, and then integrate both sides. And this would give you an implicit solution, right? Of course, just saying that and actually doing it are two different things. By the way, when you go to do this analytically, you should automatically say good for these solutions are true or good when f of y is not equal to 0. Because when f of y equals 0, we have equilibrium solutions. Okay, and so those are found separately. Sometimes you can get the equilibrium solution by a choice of constant in this, but sometimes you can't. Okay, so that's just something to keep in mind, that when you, as soon as you divide by f of y, you want to double check your conditions. Good. Okay, so now before we get into some of the models, I just wanted to mention, if y prime is equal to f of y, that means the slopes depend only on y. Slopes depend only on y. So therefore we're going to consider a new graph. And the new graph that we're going to think about is graphing y versus y prime. Right? Because the slopes, for every y on the number line, I should be able to compute y prime. So for example, I could have something like this. Okay, now what does this graph tell me? A, can you find the equilibrium? Well, we're looking for where y prime is equal to 0, and so those y's are those 2 points in this situation, or in general, it's the y-intercepts of the graph. And remember now, when I say y-intercepts, I'm talking about the horizontal axis, not the vertical axis. Okay, I'm talking about the horizontal. Good. B. If y prime is greater than 0, what can you say about y? Do you remember from calculus? Y is increasing. If y prime is less than 0, then y is decreasing, right? And so what this means is, in your graph here, for the y values between here and here, right, y is increasing, and then for these y values, y is decreasing, and for these values, y is decreasing. Okay. Now the question is translate this to a direction field. So just for the sake of being explicit here, how about this is 1 and this is 3? Okay. So in the ty plane now, I've got an equilibrium solution at y equals 1 and an equilibrium solution at y equals 3, and I didn't leave myself enough room. Okay, now we said between 1 and 3 y is increasing, so that's in this region, right? Y is increasing, and so as it turns out, it's going to look something like this, and we're going to show that in just a second. And then we're going to have decreasing functions on either side. So on this side we're going to have solutions that are decreasing, and on this side we're going to have solutions that are decreasing. Okay, and so there we go. This is an example of the direction field for this differential equation. Actually, this is a plot of possible solutions to the differential equation. Okay, so just as a quick summary then, if you're looking at y prime equals f of y, then you can graph the function f of y in the y prime y plane, or I should say y prime plane. Okay, and from that you can get these pieces of information. You can talk about the equilibrium, you can talk about where the function is increasing or decreasing, and now we can also translate that information to the direction field. Okay, so the next piece is going to be that we want to we're going to go back to this graph, the top graph here, and we're going to try to classify equilibria. Classify equilibria. Okay, so let's see how we're going to do that. I'm going to draw a new picture, get out of this one here, and so some examples of equilibria in the y prime plane. Now remember, to have an equilibrium solution, that means you're crossing the axis, right, at some point A, and so how you cross is going to show you what kind of equilibrium solution you have. So we could cross this way, going up. We could cross down. What are some other ways we might cross? We could just touch, or we could just touch going this way, right? What's another way we might cross? We might cross like this, where we have a little plateau here at A. Okay, so can we determine the stability of the equilibrium in these 3 cases, or 4 cases, 5 cases? Well, here's a hint. If y prime, these are plotting y prime, by the way. If y prime is positive, that means you're increasing, your y value is increasing. So it's nice to be able to put arrows that are increasing, and then these arrows are decreasing. And so you can probably tell right away, right? In this case, solutions are moving away from the equilibrium, and so this equilibrium is called unstable or a source. Okay. Now let's compare that to the next one. In this case, we have our solutions are increasing. On this side, they're decreasing. So what happens here in this situation is all nearby solutions are heading towards the point A. And so in this case, we would say that that A is stable or a sink. And so just to do a quick example, in this situation, right, we saw that solutions were moving towards y equals 3, and so y equals 3 was called the sink or stable, and in y equals 1 solutions are moving away, and so that's our source, or you could say it's unstable. Okay, and then you might notice that there could be other ways of crossing the y-axis here. In this situation, in this fourth one, our solutions are just always increasing. In this one, they're always decreasing. So you don't get the switch, right? And so in this case, these are going to be called semi-stable solutions. Okay. And in this case, this is almost identical to this situation, right? So you can see that there's all kinds of different ways that we could be crossing the y-axis. But we're just going to mainly focus on these. Every once in a while we might run into a semi-stable equilibrium, but usually they're going to be stable or unstable. In other words, sinks or sources. I think sink and source is a better term for those. Good, I'll stop here and we'll take a look at some specific models in just a sec.